It's a great pleasure to welcome Dr. David Masiello. He's a professor of chemistry at the University of Washington. Prior to joining UW, he was at University of Florida where he got his PhD, and then you moved to Northwestern, right, for your postdoc, and then moved to Washington in 2010. David's won a lot of awards. Amongst them are the Presidential Early Career Award for Scientists that he obtained, got it from President Obama. And he's also an NSF DMREF Centered PI. And so we are really glad to have you, and hopefully we can learn a lot about fast electron spectroscopy. The floor is yours, David. Thank you.
Okay, well, thanks so much for the invitation, Krishna. Krishna and I have known each other for a long time, all the way back from when I was an undergraduate. I did my first research experience was in the group of Joe Simmons, who is former chair of MSc at University of Arizona. And it was at that time that I got to meet Krishna. So we go way, way back. That was somewhere around 1999. Anyway, so today I'm going to talk to you about some of our electron microscopy work. And I see there's experts in the audience, Peter Crozier, a collaborator, former collaborator of mine, Peter Rez, and others. And so I'm really humbled to have the opportunity to share some of my own work in this area with so many experts on the line. I'm going to talk today, I'm going to try to tell a story of mapping the transition from weak to strong coupling in plasmonic and photonic nanostructures using fast electron nanospectroscopy and a scanning transmission electron microscope. So that's sort of the big context of what I'm going for here. Of course, I didn't do any of this work. This was all done by my students. I have an outstanding group of students and postdocs. And this is a snapshot roughly from, I don't know, 3-4 months ago. And nowadays, the folks doing EELS work involve Marc Bourgeois, who's a postdoc, Elliot Beutler, about to graduate, Siamak Khorsani, Austin Nixon, Matthew Califor, and Claire West. Claire actually just graduated and is off at the University of Cambridge in the electron microscopy group there on an Isaac Newton postdoctoral fellowship. Why don't I begin? Everything I'm going to talk to you about involves a collaboration, and the collaborations almost always have 3 components to them. There's a group of people that are making things, either by nanofabrication or chemical synthesis. There are a group of people that are measuring things, and there's a group of people that are modeling things. And I'm a theoretician, and so I'm down here on this leg of the triangle, but I really want to emphasize just how integrated a team we are in all the different studies that we do. And so I want to just give some credit to a number of collaborators over the past few years. I forgot to say this, and on our end, from the modeling end, we as I hope you'll see, is that we really are inspired to create really simple models. So we're not terribly interested in doing massive computer simulations, but instead really simple models. Anyway, sorry about that. I want to give credit to a number of collaborators that I've worked with over the past maybe 5 years. Peter's on the line, Peter Crozier is here. There's a group of collaborators that typically are making things for our team. And today I'm going to talk about work that Philip Rack at the University of Tennessee has been involved in, where he's provided the nanofabrication leg of this triangle. On the characterization side, the work today is going to involve John Camden at the University of Notre Dame and Juan Carlos Adrobo, who has now resigned from Oak Ridge and has moved to my institution at the University of Washington, and he's now here in Seattle. And then we're providing the modeling and simulation leg of the triangle. Okay, so let me kind of get into modeling and what I mean by simplicity of modeling. I need to minimize a window here. Give me a second. There we go. Oh, and by the way, I hope you can see my mouse. Please speak up if you can't. So here I'm highlighting, I guess, 6 different physical systems with fundamentally different excitations or responses, every one of which the underlying excitation can be mapped onto an oscillator. And this is what I mean by simple physical picture. And so let me kind of just go through these. So in this picture here, this is a plasmonic nanoparticle, maybe noble metal nanoparticle composed of silver or gold with plasmonic excitations, an oscillation of the free electron gas with characteristic resonance frequencies. This problem can be mapped analytically exactly onto an oscillator. Down here below, I've got an MgO, magnesium oxide nanocrystal, right? The surface phonon modes of which can be mapped analytically exactly onto an oscillator. Up here in the upper right-hand corner, I have a cyclic assembly of noble metal nanoparticles of silver or gold. One of the normal modes of this structure is a head-to-tail oscillation of the dipole plasmon resonances in each particle. And by Lenz's law, they conspire to create a magnetic plasmon with a magnetic field that oscillates in and out of the plane of the page, also mathematically, analytically, exactly mappable onto an oscillator. Down here, we've got a nanofabricated pair of coupled resonators, a ring resonator fabricated in silicon nitride adjacent to a nanobeam, this bow tie, a photonic crystal, to make a photonic molecule. As you all know, the modes of the electromagnetic field, whether they're in free space or confined in cavities, can be analytically exactly mapped onto oscillators. And in the bottom 2 cases, I've got molecular electronic excitation and an excitonic excitation. These can be, in various limits, approximately mapped onto oscillators. So you can see here we've got, fundamentally different kinds of excitations, all of which have simple mathematical representations. And so this whole story that I'm going to tell you about weak and strong coupling in various settings, everything's going to come back to an oscillator. And so oscillators, as you all know, carry oscillator parameters. They have a natural frequency, they have a dissipation rate that can be decomposed into a non-radiative component and a radiative component, and they carry mass. And in all of these different physical systems, the role of mass will be a little bit different. So for example, in a photonic cavity, the mass is actually mathematically a mode volume, inherits the role of mass. Whereas for a plasmonic system, we'll find that the mass is proportional inversely to the polarizability. Nevertheless, whether it's photons in a cavity or plasmons oscillating in a metal particle, oscillators all oscillate according to oscillator equations of motion, Newton's equations. And I've written the equation down here at the bottom. You're all familiar with it. You can't tell. This could be a quantum degree of freedom. It could be a classical degree of freedom. It doesn't matter, right? You cannot tell. So for the next few slides, since I recognize that everyone on the line is not an expert in electron microscopy, and in particular in using the electron microscope to do spectroscopy, I want to walk through an example of a plasmonic nanoparticle of gold, where I've parametrized an oscillator. And I want to work through a couple of optical observables that you're all familiar with, like absorption, scattering, and extinction. And I want to contrast those optical observables under plane wave illumination to the corresponding electron energy loss spectrum measured in a scanning transmission electron microscope. So I'm going to fix the parameters, the natural frequency, the total decay rate, and the mass for a gold nanoparticle, roughly 100 nanometers in diameter. And as I was saying, compare and contrast the optical spectra against the electron beam spectra for the exact same underlying oscillator. And in doing all of this, I really want to, and this is maybe a pet peeve of mine as a theorist, but I really want to highlight that the underlying oscillator has, if you will, an eigenvalue or an eigenfrequency encoded by the Hamiltonian itself, and that's sitting right here. However, in all of the spectra that I'm showing you, which is the actual observable measured, right? The observable is a function of the eigenspectrum, But there's really a critical difference that the observable actually is sort of convolves the eigenspectrum with the forcing. And the forcing varies depending on what kind of observable is being measured. So this is what experiment measures. And this here is, what's baked into the Hamiltonian. They're two different things. And, oftentimes, maybe nature is kind and we can often directly compare an eigenspectrum to an observed spectrum. But we're going to find, as I'll show you in a number of these EALS experiments, electron energy loss spectroscopy experiments on plasmonic and photonic nanostructures, that there are differences between the two sometimes that are quite surprising. Anyway, I'll get off my soapbox on that. So let's start with the optical side of the story. This is just light absorption from a plane wave. So here's that oscillator, that plasmonic oscillator with natural frequency omega 0 tuned to this gold plasmon at 2.4 electron volts. Absorption, physically, you've got light coming in, the oscillator absorbs heat power from the field, and it's converted into some non-radiative degree of freedom, ultimately culminating in heat. So that's absorption. And mathematically, the absorption cross-section I've written down here can be expressed in terms of the polarizability of the oscillator, which has this spectral resonance position in its denominator. And that's multiplied by the ratio of the non-radiative rate taken in ratio to the total dissipation rate of the system. And because this is an observable, there's also a prefactor here, a linear monomial in the frequency omega. And so because of this additional prefactor here, you can see that the absorption spectrum peaks out at a different position, right, than the eigenspectrum, if you will, the natural frequency of the oscillator, okay? So already we can see, even just in plain old vanilla absorption spectroscopy, there's a difference. Now let's go to scattering. This is Rayleigh scattering, elastic scattering of light. If you're thinking of this quantum mechanically, this is an instantaneous or prompt second order, like Fermi golden rule process. And light comes in, scatters off the transition, putting the system right back where it started. Mathematically, the scattering cross-section can also be expressed in terms of the imaginary part of the polarizability, now multiplied by the ratio of the radiative rate to the total rate. This is sort of a strange form that you might not be used to seeing. You're probably more used to this form here, where the Rayleigh scattering goes like the square of the polarizability times the frequency to the 4th power. So you might wonder, where are these extra factors of frequency hiding away in? And they're hiding here. The radiative decay rate this is the Abraham Lorentz decay rate, which is frequency dependent. So that's where they're going. Again, you can see that the peak in the scattering spectrum is different than the peak in the absorption spectrum, and both of which are different from the natural frequency or eigenfrequency of the underlying transition. The sum of the two is extinction. And in the diagram here, this goes back to a first order process according to time-dependent perturbation theory. If you're thinking quantum mechanically, light comes in, drives the transition, and then where that energy goes, we don't keep track of it anymore. It goes into some combination of non-radiative and radiative pathways. That's extinction. We're now ignorant over where that energy went. And so the extinction just sums the two, absorption and scattering. And so I'm just taking those two expressions from the previous two slides and adding them together. And now in the numerator, this is just the total rate divided by the total rate is unity. And we get back to the familiar extinction cross-section, which I'm showing here in black. Okay, so these are things that everyone on the line knows and understands, but I just wanted to have a common ground to move forward on. So now I want to talk about the inelastic scattering of a focused electron beam off the exact same oscillator. And so that's what this cartoon is here. This is an electron beam moving past the sample, the sphere of gold, let's say. As the electron, it's uniformly moving past, it's dragging along an evanescent electric field that is indicated by this sort of gray dashed line here. I've written down here at the bottom mathematically the form of that electric field Fourier transformed into frequency. And I want to make you aware of a couple of things that are really important. One is that there are components of the electric field along the propagation direction of the electron beam itself, as well as in the direction r hat that's in the impact plane perpendicular to the trajectory of the electron. Also, I want to make you aware, these are K modified Bessel functions, K0 and K1. They behave like decaying exponentials, kind of like this dotted gray curve that you see here, which spatially localizes the field of the electron right around the trajectory of the electron itself. And then we're looking in the Fourier frequency domain, and what you see here is that the spectrum carried by the electron's field is super continuum. So let me kind of summarize all of this in contrast to the plane wave. So in the case of plane wave excitation, right, a plane wave is perfectly monochromatic. It contains one frequency. It is spatially homogeneous over the entire wavefront. And it's polarized in the two directions transverse to the direction of propagation, right? That's the plane wave. In contrast, the field carried by the electron is spectrally broadband, is spatially localized, and has polarization components in all three spatial directions, as you see here. So these are severe differences between the two different probes, and they're in some sense like opposite sides of the Fourier coin with respect to both space and color. And so because of these severe differences, we're going to find that they act really as fundamentally different probes in what they can see and cannot see. And so with respect to a target specimen. So let's go back to the same transition that we were talking about before. And now I'm passing the electron beam by. And I want to talk about electron energy loss spectroscopy. So it turns out that ELS for short, is an extinction measure. So the electron beam goes by. Actually, most of the electrons go by and don't interact at all with the sample. But every now and then, the electron passes by and hands over a quantum of energy to the target, thereby exciting it and decelerating the electron in the process. And so in the microscope, the ELS detector is detecting that small amount of energy loss. To give you some numbers on this, like this excitation, I've already forgotten, I think was around 2 EVs is what I had chosen. The electron beam in the microscope could easily be at 100 kilo electron volts. But after this process, where the electron hands over 2 EVs to the target to excite this oscillator excitation, it would then hit the detector in the microscope now at 100 keVs minus 2 EVs, so that there's a deceleration or energy loss. That's what's being detected. And by conservation of energy, that implies that that amount of energy, 2 EVs, was imparted into an excitation or resonance of the target. And however, where that energy goes off to, the ELS experiment is not keeping track of, right? So what that oscillating dipole, its ultimate fate, whether or not it maybe liberates that energy back to the electromagnetic field or stores it in the near field as heat, the electron that passes by is ignorant of exactly the fate of that energy loss. And so down here, I'm showing mathematically the electron energy loss probability. That's this funny symbol gamma ELS. And as I mentioned, it's an extinction measure. It also tracks the imaginary part of the polarizability of that transition, but now is multiplied by a much more complicated spectral prefactor that has both space R and frequency omega dependence. And where is this coming from? It's coming from the field profile of that fast electron probe, right? Which is just fundamentally different from that of photons in a plane wave. I've also, I'm showing you the electron energy loss probability for that exact same oscillator with an eigenfrequency at 2.4 electron volts. as the dotted black line. In red is the polarizability, imaginary part of the polarizability here. In blue is the spectral prefactor, and in black is the product of the two, which is actually observed. Now, I've actually picked a really extreme set of impact parameter here to really accentuate this kind of wonky looking EELS profile in this case. And just to emphasize that one has to really carefully think about modeling the observable as well as in addition to the resonances or eigenstructure of the target itself. So maybe again, I'll get off my soapbox on that. So here's just sort of the summary of everything I just said, comparing the two. And so I'll kind of skip past this since we've gone through it carefully now. And I've turned off everyone's camera here, so I don't see you. If you have questions, just speak up, because I can't see you if you raise your hand.
David, this is Krishna. We usually reserve all the questions till the end.
Oh, the end. Okay.
We asked them to ask the questions in the chat box, but you don't have to answer it till the end of the question.
Okay. Thanks. And I don't know that I'm seeing a chat box, so yeah, maybe we'll just save them for the end then. But or just speak up. I don't mind if you interrupt me. Okay, so now, again, I apologize for the experts on the line, especially the folks at ASU. But let me go through some other aspects of the electron energy loss spectrum and spectrum image. So showing an old paper from years ago that I did with John Camden, where we measured the EELS spectrum of a plasmonic rod. I think this was silver. You can see here in the picture. And in the spectrum here, we're looking at two EELS spectra acquired at two different impact parameters, both in an aloof geometry. Aloof meaning passing external to the sample, not penetrating it. The point spectrum at position 1 is in black, and in position 2 is in red. And I forgot to say this, but this is worth emphasizing, right? A 100 kilo electron volt electron has a corresponding de Broglie wavelength that is, deeply sub-diffraction limited. It's below an angstrom. And so the electron provides an, highly nano-localized probe in which you can not only do microscopy, but also spectroscopy, spatially resolved spectroscopy. And it's not subjected to the diffraction limit of light. And so these are two different so-called point spectra. And when the electron beam is on the end, notice that it's exciting a progression of resonances. I'm going to call them dipole, quadrupole, hexapole. These are excitations of the free electron gas, plasmonic excitations in the silver nanorod that sort of behave kind of like particle in a box. You have, this progression, nodal progression, if you will, of standing waves that fit inside of the box defined by the length of the rod, the long axis of the rod. And then at position 2, it's important to note that the dipole mode is absent in the spectrum, but you do see the other modes. And so let's talk about what's going on there. So the other thing you can do in the microscope is you can raster scan the electron beam not only at these two positions, but everywhere in this region of interest. And at every single point, measure an electron energy loss spectrum. And then with this set or collection of electron energy loss spectra, we can now slice through all of them at 1 electron volt, the position of the dipole plasmon resonance, the longitudinal resonance in the rod. And what you're seeing right here is what we call a spectrum image. It's a spatially resolved electron energy loss probability map. So you're actually viewing the probability in space for the initially 100 keV electron to lose 1 electron volt into an excitation of the target. And so this is not an electric field or a near field. This is a probability. And you have high probability for the electron to lose 1 EV of its initial 100 keV at the ends, and very low, essentially 0 probability in the middle. And so let me also walk you through how that works. And it's really very simple. So here I'm showing you the field profile of an electron parked right here in the impact plane. If you remember from freshman physics, all the electric field lines flow inward because it's a negative charge. And then you also remember the Lorentz force. The Lorentz force says that force is charge times field. So when you park the electron beam at either end, right, here on the right, that's exerting a force that pushes the free electron gas of the conduction band electrons in silver, pushes them leftward. And then they start to oscillate back and forth at the characteristic resonance frequency of the dipole longitudinal plasmon resonance of the rod. Equivalently, one could put the beam over here, and due to the symmetry of the rod, the exact same thing happens. However, if you put the beam in the middle of the rod, like where my mouse is, now, according to the Lorentz force, that would be pushing the electron gas radially outward, imposing a nodal line in the middle. And unfortunately for the dipole resonance, that's exactly the worst place to put a node, right? The dipole mode does not have a node there, right? And so that's why the probability goes to 0 in the middle. However, if we now move up to the quadrupole mode, right around, I don't know, 1.9 or so electron volts, and we do the exact same slicing through all these spectra, EEL spectra at 1.9 eV, now we see the probability map, the spectrum image of the quadrupole, longitudinal quadrupole mode, which is now bright in the middle, right? Which is exactly the best place to put the electron beam to exert this force that pushes the electron gas outward, oscillating with a nodal line in the middle, right? And so it's through a combination of spectroscopy and spectrum imaging that we sort of gain new insight about the target and its excitations. And so now I want to use this insight to start analyzing a couple of different scenarios in both weak and strong coupling. So that's where we're going. And what I mean by that is weak and strong coupling between particles mapped onto oscillators. So here's my cartoon, got two oscillators now, and they're coupled with some coupling strength G. And let's talk about these two regimes. So first is the regime of strong coupling. This is the hybridization regime. It's the regime, depending on the community I'm speaking with. If it's chemists, they'll talk about molecular orbitals built out of a linear combination of atomic orbitals. If I'm talking to engineers, they might talk about normal modes or super modes, or physicists, normal modes, super modes, it's all the same stuff. Physically, what's going on here is that the coupling strength G, or the coupling frequency, is large compared to all of the decay rates in the problem. So you have two masses here coupled by some common spring. And if I were to come here and poke mass 1 and get it oscillating, then energy will coherently flow over to mass 2 and then back to mass 1 many, many, many times before it leaks out to the environment, through the decay rates gamma 1 and gamma 2. So that's the regime of normal modes, where now these oscillators start to oscillate. If you can see my hands, in an in-phase manner and an out-of-phase manner, are the two fundamental normal modes of the system. Mathematically, we can describe this in the usual way. You have one oscillator, we have another oscillator. In this case, I've got them, coupled with, just coordinate coupling, or, mu dot E coupling that we're all familiar with. This is in the coupled mode basis, but of course we can mathematically transform to the uncoupled basis of normal modes. Again, the in-phase bonding oscillator and the out-of-phase anti-bonding oscillator, which are now uncoupled. And the degree of coupling is dictated by a mixing angle. And down here on the bottom, I'm showing the mixing angle. And physically, you can think of it, the mixing angle is, goes like the arctangent of G, the coupling strength on the detuning. And so, for example, if the detuning, sorry, I need to move something out of the way here. I've got a window blocking me. There we go. So if G on detuning, let's say, is small, so the coupling strength is small compared to detuning, then the arctangent goes to 0, and so mathematically the in-phase and out-of-phase oscillators just return back to the 1-2 basis oscillators. They're sort of unhybridized, and then in the small detuning limit, large G limit, the arctangent goes off to pi on 2, and there's another factor of 1/2, making it pi on 4. And so then we have equally weighted superpositions of the 1-2 oscillators, creating the supermodes plus and minus. And I forgot to say here, where this is all assumed to be in the limit where G is large compared to dissipation. And so in that limit, I've neglected dissipation completely. It doesn't appear in the Hamiltonian. This is a Hermitian Hamiltonian. Okay, let me keep going. So we can picture this with spectra. So here's a pair of absorption spectra for 2 uncoupled oscillators initially, and then I can rope them together and couple them strongly. And the resulting normal mode spectrum is in black with the characteristic Rabi splitting between the in-phase omega plus and out-of-phase oscillators. So that's the picture of strong coupling, the hybridization spectrum. I now want to also talk about weak coupling, and then I'm going to do some specific examples. This is the case where now the coupling strength is small compared to the dissipation rate, such that if we now push on one of the oscillators, one of the masses, I should say, energy will go to the other one, but won't come back. It'll just leak out to the environment. And in particular, in today's talk, I'm going to talk about the Fano regime. This is the regime where not only are we in weak coupling, but also one of the decay rates is very large, like a factor of 10 larger than the other decay rate. And here's a picture of this regime here, where we have sort of a quasi-continuum mode Q1 and a quasi-discrete mode Q2, and they're now weakly coupled together. And I'm showing you in black the composite spectrum, the absorption spectrum, taken in ratio to the spectrum of just that blue background mode. And as I will explain later in the talk, Ugo Fano back in the 60s studied this problem within the context of helium autoionization and sort of worked out all of the basic physics of what was happening here within that context. In that context, a similar asymmetric spectrum was generated or was observed that I'm showing here in the context of just 2 oscillators. And this asymmetry or cutout in the spectrum occurs exactly at the overlap of the quasi-discrete narrow mode and the lossy quasi-continuum mode behind it, and heralds the spectral location of essentially one directional energy transfer from the quasi-continuum mode to the quasi-discrete mode where the energy is stored. So you could sort of physically imagine that you push on this oscillator, energy goes over to mass 2, and it continues to oscillate, but doesn't ever come back. Kind of a strange scenario. And Professor Fano years ago, through his genius, was able to encapsulate mathematically the behavior of this asymmetric line shape completely in a so-called asymmetry parameter Q that can be positive, negative, or 0, and depends on the detuning between these 2 modes, as well as a generalized frequency epsilon. And so we'll come back to this later in the talk. But anyway, that at a high level, we've talked now about strong coupling and weak coupling. And so now let me give you some specific examples. And this is some slightly older work of mine that I'm going to highlight just to tell this story. And so here I'm looking at a cyclic assembly of noble metal nanoparticles. These are sometimes called plasmon oligomers or magnetic metamolecules. Meta, if you remember in Greek, means beyond. And the reason for that is each of these particles might be silver or gold, any of the coinage metals. And as you know, coins or jewelry is not magnetic, right? The permeability is essentially that of the vacuum. However, if you create a cyclic assembly of such particles, like I'm showing here, there is a normal mode that I'm indicating a head-to-tail bonding arrangement of all the electric dipole plasmons, which collectively conspire to create a mode that has magnetic response. That's actually pretty substantial. And that's what I'm indicating in this cartoon. M is the effective induced magnetic dipole moment from this that goes together with this cyclic oscillation of the electric dipoles. So in this case, meta, the oligomer has magnetism, optical frequency, in fact, magnetism, when none of the individual components do themselves. Spectrally, I'm showing two different point spectra. I think of this triangular assembly, actually it's a slightly different one here, it doesn't much matter. And I think the critical thing is depending on the impact parameter, for example, at position 1, you have the right symmetry to excite this magnetic mode. It truly is a new eigenmode of the system, and you can see it's pronounced in the spectrum. Okay, so what do I mean by strong coupling? So we had this idea of, well, can we take one of these oligomers and another oligomer and bring them together and hybridize them, just like you would, like in general chemistry, take two hydrogen atoms with their s orbitals and bring them together and make H2 with, sigma orbitals that are molecular orbitals that are delocalized. Could we do the same thing here with two atoms, one being one oligomer, the other being another oligomer, and strongly couple them? And so this actually started a long time ago, I guess, in 2014, where we started building these like complex assemblies of cyclic assemblies of particles. And these sort of look like benzene and naphthalene and whatever this thing's called. I don't know. I'm not much of a chemist. I'm sorry. But they're not, right? These are like gold nanoparticles, and they might have a radius of 50 nanometers each. So these are really quite large structures. And so at the time we went through and just, did this oscillator game, like I've been telling you about, and went through and found the normal modes of these systems. And here I'm showing you that big one, and just sort of a selection of its normal modes. And it's really very interesting. So the arrows here are the eigenvectors, and the colors that you see are the out of plane component of the induced magnetic field. And you can see that the normal modes, I guess 1, 2, 4, 5, 6, 7, sort of look like what you would have learned when you studied the Huckel theory of benzene. That you have a singly degenerate lowest molecular orbital and a singly degenerate highest, and then you have a pair of doubly degenerate and doubly degenerate modes in between, and they have various field structure and nodal structure and have both ferromagnetic and antiferromagnetic character. Higher up in the spectrum, there are also like giant radial breathing modes and really, really rich physics in these systems. The downside, though, this was all done theoretically, was that when we looked at the EEL spectrum, it was a mess. Like there was no way that all these modes are densely congested at the low energy part of the spectrum. And there's just no way that we were going to get our experimental colleagues to go in the lab and measure the spectra of these like clusters of disks or spheres. And so then we had this idea a few years ago is like, rather than use disks or spheres, in the case of spheres, all three dipole plasmon modes are degenerate. Instead, if we use rods, that then detunes one long axis mode separately from the other two that are transverse on the short axes. And so it just provided a way to decongest the spectrum. So then we were able to finally like realize this idea of strong coupling or magnetic dipole hybridization in these oligomer systems. And so this was again with Philip Rack and John Camden. Years ago, we brought together two oligomers through a series of experiments. And here I'm showing you in that strong couple limit, the spectrum images for, you can see my hands, we've got one magnetic dipole on the left oligomer, one magnetic dipole on the right oligomer, and as we bring them together, they hybridize into an in-phase oscillator and an out-of-phase oscillator. And so that's what you're seeing here, the north-north and the north-south in-phase and out-of-phase oscillators, and at their respective energetic locations. And if you know how to read the tea leaves of the spectrum image, which is what I was trying to explain in those earlier slides, you'll see this is exactly the kind of telltale sign for a dipole-dipole in-phase bonding mode, north-north. And then with this big, bright probability region in the middle, the exact sign that you're looking for the Ada phase, north-south mode. And we did this both in a homodimer, a magnetic oligomer homodimer, but also like H2, but we also broke the symmetry like HF, hydrogen fluoride, and examine that case as well, where now the normal modes bias one way or the other due to the effective polarizability difference between the two different oligomer units or atomic units, if you will. So that's my strong coupling story. I now want to go to the weak coupling story. And again, I mentioned this goes all the way back to Mr. Fano, who is on the faculty of the University of Chicago, I guess at this time of this paper at what is now NIST. And he was examining the autoionization spectrum from a gas of helium using eels, interestingly, measured by Silverman and Lassiter in 1959. They observed these sort of strange asymmetric line shapes. The physics of what was going on here, this is a double excitation, a 2s2p double excitation in helium that's now above the first autoionization continuum. And so that excited state configuration can mix with the continuum, providing two different pathways. And so Fano worked through the physics of the configuration mixing in these two cases of a discrete transition interacting with the continuum, was able to mathematically derive a spectrum, a reduced spectrum, if you will, that had this particular form. And he sort of encapsulated all of the complex physics of this process into a single parameter Q that I mentioned earlier. It can be positive, negative, or zero, that completely describes the asymmetry of the line shape. Does it go up and then down, or down and then up, or is it perfectly symmetric? Those are the different cases. And so this was quite a while ago that this work was done, but as I'm sure you're well aware, for the past decade, Fano processes have been very popular in the plasmonics world. And we got involved in this back in 2013, again, from a purely theoretical perspective. And we cooked up a system, a plasmonic system, where this mixing of a continuum and a discrete mode, or quasi-continuum and a quasi-discrete mode, might be able to be evidenced in the electron microscope. And so I like to show this. This is an old picture now, my son from back in 2013, and his buddy, as two oscillators. And one is driven and one is static. So my wife is forcing him here. And so this boy is at rest. However, if a rope were to connect the children, providing a weak coupling link, then the energy can flow from this swing into the other swing. And in the Fano regime, this child would be oscillating and this one would be at rest, even though this one is the one getting driven. So it's kind of a strange scenario, sometimes referred to as an interference process as well. I want to avoid that language for technical reasons, though, which if someone wants to hear about that, we can discuss later. And so the system we cooked up was a mixed metal. Again, this was purely theoretical, palladium and silver. The palladium having a big, lossy, broad dipole plasmon resonance here in this red color. And then we tuned the rod length of the silver rod so that its quadrupole resonance, which is quite narrow, spectrally overlapped the palladium dipole. And so down here, this is all done theoretically. You can see the eel spectrum in red, measured at position 1, and that's really critical. So the electron beam measures a different spectrum depending on where it's located, and it was only at position 1 that we found theoretically and numerically that we were able to get this sort of characteristic eels-like asymmetric line shape. Unfortunately, that system, being that it was composed of two metals, was just not none of our collaborators were able to make that by nanolithography or even synthetically. And so we sort of went through a period of time where we forgot about this system. And then it was, I don't know, maybe in 2018 or so, we approached it again with what we are affectionately calling a lollipop made of gold. all one metal that could be nanofabricated. So here's an image up here. So in this case, Philip Rack did the nanofabrication. And so what it's composed of a disk of gold. It's quite large, about 250 nanometers, if I remember correctly. And it has a big, lossy, broad plasmonic dipole resonance. So that's going to inherit the role of the continuum channel. And it's described by the dipole moment P0 mathematically. And we put that disk, we fabricated it adjacent to a very long wire of gold, which can be a few microns long. And in that limit, a wire of gold, its plasmonic resonances actually evolve into Fabry-Perot photonic resonances. So they actually are more light-like than matter-like. It doesn't really much matter. I think the critical thing is that there's a progression of high-quality Fabry-Perot oscillator modes that live on the wire. And one of those modes, I'm going to call, it has a dipole, an induced dipole, I'm going to call that 1. And so here, again, to give you a sense of modeling, writing down the oscillator equations describing the interaction between these two objects with their own intrinsic non-radiative damping, with radiative damping, different natural frequencies, and frequency-dependent coupling. And we're going to position the electron beam here on the end of the disk, right, driving the continuum channel, the continuum mode. So the forcing is only on the disk. And then there are two regimes, right? There's the strong coupling regime, the weak coupling regime. And how do we control them? Where the experiment lies, it's controllable by the gap. So over the course of nanofabricating lots of different lollipops with lots of different gaps, we can move between these two regimes. And in particular, if we further are in the limit where one gamma, one loss is large compared to the other, as we are in the system, then we further enter into the phono regime. And so we showed mathematically that the loss function gamma of the dimer, if you will, taken in ratio to the loss spectrum of just the continuum channel, the disk, can be repackaged into a form that looks like Mr. Fano's form, but additionally has a term due to the fact that the quasi-discrete channel, P1, also has loss in it. So in Fano's case, the 2s2p double excitation, he assumed to be completely discrete, lossless. And so he didn't have the second term. Nevertheless, that's sort of a technicality. And so this actually took it was probably one of the most frustrating scientific experiences I've had, with lots of back and forth between fabrication, characterization, and modeling. But this is sort of what we were going for, theoretically. This is what we were looking for. And in particular, in the weak coupling regime is really where we wanted to try to see these characteristic phono anti-resonance line shapes that, again, are produced by the weak coupling between the Fabry-Perot photonic modes of the wire here in black, coupling weakly to the continuum or quasi-continuum in dashed gray of the disk. And in red is the composite dimer spectrum with all these asymmetric line shapes, some with positive Q, some with negative Q, and some even with Q equals 0. This was what we wanted. Of course, there's also the strong coupling case, which is actually pretty easy to find, where you have Rabi splitting and supermodes formed between the individual disk and rod modes of the dimer. And so after a lot of back and forth, and I was inspired by this quote down here: problems worthy of attack prove their worth by fighting back. So this one really fought us for some time. We eventually figured it out. And so you're seeing the experimental observables here, the Fabry-Perot modes of the wire by itself, the dipole plasmon of the disk here as this low energy feature in blue, and then of the dimer, you now see the composite phonospectrum with all these cutouts at the exact spectral locations where energy in a one-directed manner is shuffled over from the electron beam exciting the continuum disk, which then hands the energy over to the wire, which has these high-quality photonic modes, and the energy ultimately dies there. It doesn't come back. And so, in the rest of this paper, we did analysis of this problem, and mode by mode or anti-resonance by anti-resonance, we're actually able to fit and extract the Q, the phonoasymmetry Q parameter for every one of these modes. And ultimately, after, I call this the junkyard, after fabricating lots and lots of different lollipops, both as dimers as well as their individual components, we were able to piece together sort of a broad view of the lay of the land, and really do a thorough analysis of like where the phono regime really was, and this sort of much larger gray area where, which was sort of phono-like, but technically not truly phono. And that sort of comes down to technical minutia stuff that I'm happy to talk about later, if one is interested. So this was really a heroic experiment that really went back and forth between nanofabrication, characterization, and theory, with Philip Rack doing the fabrication, and Juan Carlos Adrobo and John Camden doing the characterization at the Oak Ridge National Lab. And so lastly, I think I'm right about on my last slide now, conclusions. I started by comparing and contrasting optical versus electron beam excitation of the same oscillator system. I emphasized the importance of modeling the observable itself and not just the eigenspectrum. And that was really critical, for example, in extracting those phono Q parameters, right? We needed to actually have a mathematical model of the observable in order to fit the observable to the observable, right? Not the observable to an eigenspectrum. And we looked at two different examples from strong to weak coupling, magnetic plasmon hybridization, and phono anti-resonances. And so lastly, I want to thank all of you. Thanks to the organizers, both at U of A and ASU. Thanks to the funding agency, C's plural. This was originally funded by DOE and now has been picked up by the Air Force Office of Scientific Research. And also I want to thank my group. This was a photo from, I guess, last summer. Most of us were together, except my two postdocs that weren't able to attend. And of course, they're the ones who've done all of the work and really deserve the credit for this. So thank you again. I'm going to stop my slideshow, and I'm happy to take questions from the audience. Thank you all.
Thanks, David. Very enlightening and
welcome.
Really, really thorough. We really enjoyed it. And I think there's a question that's already been posted by Peter Rez. I think this probably goes back like 20 slides, but anyway.
Okay, sorry, I didn't see it. Yeah,
David,
could you read it out loud?
David, when you did the thing with the K0 and the K1, and you said you chose an extreme value of R, what was it?
Oh, good question. Let me go back. I thought, you should ask that question. I made these slides years ago. So let's see, where can I find it? Is this it? No. Here it is here. Good question. I think it's a pretty far impact parameter. It's like 100 nanometer diameter gold sphere. And I think the impact parameter is also quite far out. I don't recall. It's maybe on the order of the diameter itself. I'd be happy to rerun the calculation and tell you exactly.
No, I could run it too. No, I wanted to say that was a truly wonderful talk. I really, really enjoyed it. I love your simple models. I also just have a couple of comments. The canonical examples of phono resonances and eels are the M23 excitations in the transition elements and the M45s in the rare earths, where you get this mixing between a bound state and continuum state, and you get this massive enhancement, which actually makes it the N45s the edge to go for when you're trying to detect a rare earth. So I also wanted to say that I did this thing where I thought of the core exciton in things like lithium and beryllium as another example of a potential phonoresonance. What happens is you remove an electron, you pull down some levels, and you can get them mixing. And I wrote a paper for PRL about that. I mean, it kind of looks very similar to beta salpeter, but it got bounced by PRL and I never pursued it. But I still think it's probably right that you can think of a lot of core excitons in a finite resonance picture.
Yeah, no, fascinating. I hear, and these are at much higher energies. But yeah, I hear you. It sounds fascinating, and we could go off on PRL separately. That's a different story. But you know, I'd love to, if you wanted to chat more about it. We're kind of on
we could resurrect it.
We're on a bit of a hiatus right now
John
from Fano, but I'd love to get back into it
because he was very big on the beta salpeter view.
Yeah,
I mean, I called it the giant core hole resonance because of the enhancement. But I think it's probably right. I'm going to be in Seattle later in the year, so I'll get together then.
Oh, please reach out to me. Yeah. Great. Thanks. Yeah, thank you, Peter.
Maybe Krishna, maybe I could jump in with a question as well. Yeah. Again, I want to, David, again, I've heard you give this oscillator presentation several times and I love it. And I want to say to all the graduate students, go back to freshman physics and remember those coupled oscillators with two pendulums or springs, reread that stuff because actually it comes up everywhere. And I love the fact that you strip it down to that very simple way of thinking. And I mean, it doesn't capture every aspect, but it captures 90% of it. I wanted to ask you, you know, I loved listening to the presentation about strong and weak oscillators. And of course, you know that we're always, we do all this photocatalysis, you know, where we're trying to transfer energy from one place to the other. I mean, a lot of energy conversion is doing that. And of course, in quantum, they have this whole transduction thing as well. I wanted to ask you, in terms of directional energy transfer, is it true to say that if you have strong coupling, it's not directional, it goes back and forward all the time. But if you have weak coupling, that's how you could transfer the energy in one direction. Is that correct, or that's not true?
With largely correct, with the additional constraint that you have to have a difference in line width. So if you have a high quality mode, it's long lived. Right. So you want to really funnel energy into that mode with a high quality. So temporally, it just stays there. Right. And so I think those are like the secret spices to get it to work. Yeah.
Yeah.
Thank you. Maybe thanks. The other Peter maybe had a hand up too. Did you have a comment, Peter Rez, or no? Oh, okay. I thought I saw you waving your hand. Okay.
David, when they do the optical spectroscopy and when you simulate it, does the background material in which these are matter at all?
Yeah, that's a great question.
Talking about the coupling.
Yeah, so thank you, Krishna. I could go off on this. So my talk today largely surveyed papers from a few years ago, and I didn't talk about our more recent stuff because some of it's fairly technical. So we just wrote a paper, I guess, last year with Maureen Lagos at McMaster University, another electron microscopist. This is a theoretical paper where we're looking down in the far IR. And in that part of the spectrum, I guess I want to contrast two things here. So here I'm talking about largely the visible part of the spectrum and largely plasmonic excitations, where the background, in this case, like the TEM grid that the particles sit on, is spectrally pretty boring. Right, you know, it's maybe providing a slight shift of the intrinsic the free space, if you will, plasmonic resonance. And why is that? It's due to the image effects. Like a plasmonic dipole will now see and weakly interact with its image in the substrate below, and so there is a little bit of dressing that happens, and a slight little bit of shifting. There can be, depending on the refractive index of the substrate, if the index is high enough, then there can be image-induced mode mixing, where in free space, for example, all of the plasmonic modes are orthogonal to each other, they're normal modes. However, if you now land the particle on a substrate where all of the different multipole modes see their images, then they not only can be dressed by their own image, but now that breaks the symmetry and allows the originally orthogonal free space modes to mix with each other. But it's usually a very weak effect. Okay. However, when you go down into the IR, right, where now you have maybe MgO particles with surface phonons sitting on an MgO substrate with Fuchs Cleaver modes, now you have like both the particle, the specimen, and the thing that's holding it, which you normally think of as being passive and boring. Both of them are like active dynamical players in the story. And the nature of the probe and the way, so the probe as an electron, unlike light, I think of the electron probe as like the delta function sourcing a Green's function. I mean, it is a little delta pulse that exposes the full induced Green's function of the target. It sees everything. So you really have to, I mean, not to go, it's a whole nother talk, especially as you start getting into regimes where like the substrate itself is resonant with the excitations on the target. You really have to deeply think about what the observable is measuring. And one of my collaborators told me this. I think it originates with Dick Zare at Stanford, that an experiment always measures the exact answer. It's just the answer to what question you don't know, right? And so this is a great example of that. They hear that in this regime, the electron probe is measuring something, but just what is it measuring, right? And so you really have to think carefully in certain parts of the spectrum.
Cool. Okay, so it is at this frequencies we don't have to worry as much as
here it's not so much of a big deal. Yeah, so here if it's a silicon nitride substrate, it's going to provide a slight shift, but not much of anything beyond that.
Yeah. Okay, cool. Any other questions, comments?
Yeah, can I make one more comment?
Oh yeah, go ahead, Peter, sure.
Yeah, I just wanted to point out there's a really recent elegant experiment of Maury in Lagos. It's a kind of more of a strong coupling mode where he has a nanorod coupled with kind of like the optic phonon or maybe phonon polariton modes in an insulator. I assume you know that paper. And the other thing is a crucial difference between electrons and photons is photons, you have a magnetic field perpendicular to an electric field related by the speed of light in the medium. With electrons in the regime we're at, normally we're doing a lot of our experiments now at 60 keV, it's basically all electrostatic unless you're in a Cherenkov regime. So there's some interesting similarities and differences.
Mm-hmm. Yeah, thank you, Peter. Absolutely. And it is those differences that are just so interesting, right? I love trying to dig in and figure them out and write papers on those differences. Yeah, thank you.
Anyone else, guys? Please either ask in the chat or now's the time to ask David.
Yeah, pretty easy to find too. You can always email me.
Yeah, no, this was great, Peter. I think there's a lot of overlapping interest within lots of work that's going on in optical sciences and physics here too, on these areas, both on the imaging side and in general nanophotonics too. So I think my hope is that the folks who couldn't make it to the talk will watch it on YouTube and probably get back to you soon. But nevertheless, there's a lot of interest both at ASU and UFA to continue these discussions. There's I think there's enormous scope here for possible collaboration. So David, let us know when you're available for travel. We would love to host you in person.
Oh, thank you. I'd love to come. Thank you very much.
I think maybe for the next few months, you're better off avoiding this area, at least starting May to September. So maybe fall. It's going to be really hot. You may not.
Yeah. I'll sure. I'll take your word for that. Yeah. No, let's be in touch. I'd love to come and visit both the folks in Phoenix and in Tucson.
Yeah,
and I won't get involved in any rivalry.
Oh no! Now we are best friends.
We're all good friends. We're all
good. Okay.
We're trying to build bridges, stronger collaborations between the two programs. So no, absolutely, David. We would love to co-host. Yeah, that would be wonderful.
In fact, we've had discussions with Peter too to maybe even start some winter schools focused on emergent materials, topological materials.
Oh, that'd be wonderful. Yeah, and any opportunity to get out of this cloudy weather would be great. Yeah, you can see it's kind of cloudy out there. So.
Yeah.
Send some of the clouds our way. We love the clouds.
Okay. The grass is always greener, right?
Yeah, the grass is always greener.
Yeah.
Cool. Thanks, David. This was great. We will probably post it on YouTube within the next 1 week or so.
Okay. Super.
Thanks again, David.
Yeah. Okay.
Thanks a lot.
Thank you all.
I'll chat with you next week,
Great.
David.
Okay.
Bye.
Bye. Bye.